Good evening, everyone. Can you see the slides? Okay. Today we'll be looking at torrefaction and pyrolysis. So you all know what pyrolysis is. Can someone tell me?
It's when you heat something in the absence of oxygen.
Yes. So what are the products of pyrolysis?
Biochar,
Yeah, and
bio oil.
bio oil, and there's one more.
I'm not sure.
So you told the solid and liquid. What about the gaseous product?
Methane.
Methane is just one portion of it. What is released when you?
Syngas.
I mean, no, it's not syngas. Pyrolysis does not provide syngas, but even not that. So it's volatile gases. Okay. So the volatiles within the biomass are released when it is subjected to heat in the absence of air. Okay. So torrefaction, what is torrefaction? Is just a mild form of pyrolysis. That's it. So pyrolysis happens at, let's say, 600, 700 degrees Celsius. Torrefaction happens at 200 to 300 degrees Celsius. So what is the use of torrefaction? There are a few uses. We'll just have a look at torrefaction right now. So the contents for today is what is torrefaction? Then I'll be describing a torrefaction system developed at IISc. Okay. Then we go into pyrolysis, the products of pyrolysis, and the bio oil that we just talked about. What are the properties of the bio oil compared to heavy fuel oil or crude oil? Then the advantages of pyrolysis, then some pyrolysis units, and then we'll go on to the discussion. Okay. So what is torrefaction? So like I said, torrefaction is a mild form of pyrolysis where the conversion or the reaction takes place in takes place in the absence of air, of course, but at very low temperatures. Okay, around 200 to 300 degrees Celsius. The heating rate is also quite low, and the residence times are quite long. I mean, it's 10 to 30 minutes. The use of pyrolysis is it is kind of like an energy densification of biomass by subjecting it to this form of mild pyrolysis. Okay, so why do we need the energy densification of biomass? So the LHV of biomass, that is a calorific value of biomass, is between 15 to 18 megajoule per kg normally. So when we do this form of pyrolysis or torrefaction, the energy density or the LHV increases to 20 to 25 megajoule per kg. Can someone tell me why that is? Why does the energy density increase? As in, if you take 1 kg of the material, raw biomass, you can obtain about 15 to 18 megajoule of energy. But then you subject it to pyrolysis, which is a mild, torrefaction, which is a mild form of pyrolysis. And if you take 1 kg of torrefied biomass, the energy content increases to 20 to 25 megajoules. Why is that?
Because, sir, densification in the sense.
Energy densification. I mean, it's per unit mass.
Concentrated. Is it concentrated?
Yeah. Sorry?
Okay. Like the energy which is to be generated is from a concentrated biomass.
What do you mean by concentrated biomass?
Like you said here, torrefaction is energy densification by subjecting it to mild pyrolysis.
Energy densification does not mean compacting. It's not physical densification of the biomass. We're not compressing it here.
Okay.
Energy densification is we are increasing the energy content of the biomass per unit mass. That's it.
Okay, okay, sir.
So why is that? That's my question. Why is it increasing from 15 to 25? What happens? I mean, so like I said, we are subjecting it to this temperature. Now tell me, I mean, that is your hit.
Increasing the temperature kind of changes its composition, is it?
It won't change its composition. I mean, at 200 degrees, what composition can it change? On the contrary, I would argue that we are using like volatiles, which are still combustible, right? So the volatile gases that are released has some CO2, of course, but there's also H2 and CO, which are combustible. So that could contribute to the biomass energy, I mean, biomass LHV. So we are in fact losing that, the portion of it. So why is it increasing? There's one major thing that is lost during the torrefaction that kind of increases the energy density of this biomass. What is that?
So mild pyrolysis actually, what is that? It kind of prepares it like it is ready.
Huh?
Is it?
Sorry?
Like whatever energy is to be released is ready to be used up. Is it?
What do you mean by that?
Like when you first provide the raw biomass, it is
Yeah.
at normal temperature, and if we increase the temperature,
So,
it is
so
the energy
even
is ready.
so if you use torrefied biomass, you're actually not using it right there. You're transporting it. You won't transport it at 300 degrees, right?
Okay.
So obviously, you won't keep the vehicle at 300 degrees to transport it, right? You have to cool it down.
So
Yeah.
in torrefaction, we are heating it at a lower temperature, right?
Yeah.
So is it the volatile like stuff that
So like I
gets it?
said, volatile gases contain carbon monoxide and hydrogen also, which are combustible. So which we are losing perfectly good gases. I mean, to the atmosphere or wherever. If you want to reuse it, that's fine. But we are losing it from the biomass. Okay. So how is the energy content increasing? So before losing the volatiles, we lose something else. I want you to focus on that and focus on this temperature over here. Okay, what does okay, recall your lecture on biomass properties. What all does biomass contain? Hmm?
I'm
Think
not sure.
proximate analysis. Think proximate analysis. What does it contain? What are we measuring in proximate analysis? So this was covered, I think, 2-3 days ago. So what is proximate analysis? What are we measuring there?
What is
Sorry,
what is
I didn't hear you properly.
the water like the moisture?
Exactly. Right. So as soon as you heat it to 100 degrees Celsius, you're losing moisture. So if you lose moisture, what happens? I mean, water does not contain any, it's not a fuel. It has an LHV of 0, right?
Yes,
Does not have
yes.
any calorific value. And let's say the biomass has 10 to 15% of moisture. So you're losing 15% of your mass, but that is something that we don't require, something that is in fact detrimental to our to combustion of biomass. Okay. In actual, we lose about 30% of the mass of biomass because, yeah, even if you consider like 10% as moisture, the other 20% is around, I mean, the other 20% is volatile. Okay. So about 70% is retained, but then from the overall biomass, about 90% of the energy content is retained. Okay. So we're losing only 10% of the total energy content. Okay. In the way of, losing the volatiles and also providing energy for this process, right? Only 10% is lost, while um, about 30% of the mass is lost, but then the energy density of the biomass is increased. It is increased to 20 to 25 megajoule per kg. And that enables co-firing of biomass with coal. Coal normally has 25 to 30 megajoule per kg. Okay. So there is a mismatch kind of, right? So if we torrefy it, we bring it on par with coal. The lignite, I think, has 25 megajoule per kg. Okay. So the physical conditions, like I said, 250 to 300, or you can even start at 200, low heating rates and high residence times. Okay. And very important to note, torrefaction is an endothermic process, which means it requires heat. I mean, the process requires heat. Okay. And because there is no other process happening simultaneously along with torrefaction, we have to supply the heat in the form of, let's say, flue gas, waste heat, or whatever it is, or we have to burn some fuel to provide that heat. Okay. So if you have a look at gasification within the reactor itself, the pyrolysis is taking place, and the heat required for the pyrolysis comes from the oxidation zone, where the combustion is taking place, or the oxidation, which is an exothermic process. That heat is kind of emanated to the pyrolysis zone, and using that heat, the pyrolysis takes place. But in this case, there is no such process happening, so we need external source of energy for this. Okay. And another important point to note here is that torrefaction improves the hygroscopic properties of the biomass. Hygroscopic means that it is closed to any kind of moisture. So even if you put it in an area with high relative humidity, it won't absorb any moisture. So that kind of makes it easy to transport, easy to use, easy to handle, easy to store, everything, right? And another thing is it is ready to. I mean, if you just touch that kind of biomass, right? So the torrefied biomass and which is cooled, if you kind of touch it, it will just disintegrate into a powder. Okay. So if you take, for example, a straw, rice straw. So if you take rice straw in your hand, will it just become powder? No, right? It is flexible. You can maybe tear it or whatever it is, but you cannot grind it as easily. Okay. But if you torrefy this biomass, the grindability properties increase. And what is the use of grindability? So if you want to make pellets of the biomass or briquettes, have you seen pellets? Do you know what pellets are?
Yeah,
Yes,
they
yes.
make it out of wood sometimes.
Yeah. So these are like small cylindrical shaped, materials. So you can make pellets out of biomass. You can make pellets out of, let's say, polythene, whatever it is. Okay. So to make these pellets, first you have to grind the material. And the grindability of the material is a huge issue during the pellet or briquette making process. So briquette is just a bigger pellet. So pellets have sizes of about 6 to 10 millimeters. Briquettes have sizes of like 50, 60 millimeters and so on. So it's big. Okay. But for both processes, you need ground biomass, right? So this increases because there is no moisture inside. So if you touch it, it will just disintegrate. You can just grind it easily, and then you can mix it with any additive you want, and you can pelletize it, briquette it. One disadvantage is that actually moisture helps in the binding process. So yeah, there is one disadvantage over there. But in general, yes, it improves the grindability. Okay. So the torrefaction system that I was talking about developed at IISc. So I'll just come, instead of just reading this, I'll go over here directly. So there are two zones here. So this is a conveyor type, vertical conveyor type, system. Okay. So you see a straw bale. Have you seen this type of a bale? Rice straw or wheat straw bales. So after harvest, normally there are these baling machines, balers, that run on the field, and they kind of bundle it in this way, either in this way or in the form of a cylinder. So here we are using this kind of a cuboidal bale. Okay. So the bales are placed on top of a conveyor. Okay, and they are actually cut, right? They're sliced basically, and each one, like, there is a plunger kind of setup here that kind of pushes this down, and then there's another plunger here that pushes it on pneumatic. It's pneumatically operated, and then it kind of is pushed to the conveyor. The conveyor is rotating this way. So on the left side you have a drying zone. On the right side you have torrefaction zone. In the drying zone, the temperature is maintained at 100, close to 100. I mean, slightly more than that. And then there is a mechanism, lock hopper mechanism. So let me show you here. Air curtain is there. Yeah. So there is an air curtain here, so that there is no, seepage of air to this zone. Now, the biomass, as it comes into the torrefaction zone, right? And then here what happens is the temperature is much higher. Like I said, it's maintained at 200, 300 degrees Celsius. Okay. And the biomass is torrefied. So now here we have a lock hopper mechanism. Then we have a conveyor again over here. So the biomass here is at more than 300 degrees Celsius. So on this conveyor, there is a spray of water from a water tank above. So what happens? The water just evaporates as soon as it falls on this, but the biomass does not absorb any of this water because of its hygroscopic nature. But this is cooled down. So why? Let me ask you this before I proceed to explain the rest of this diagram. Why do you need to cool this biomass down immediately?
So that it doesn't release the energy, or it doesn't start burning.
Exactly. It should not start burning because it is at a very high temperature. It is very much possible that it is the temperature is above its ignition temperature. Okay. So, or it could also get pyrolyzed more, which we do not want. Okay. So we kind of spray water on it, we cool it down to a safe temperature. Safe temperature is even anything less than 150 degrees Celsius. We're okay with that. And then it's collected somewhere. So how are we providing the energy for the drying and torrefaction? So let us look here. There is some heat source. The heat source could be anything. Okay, so it could be direct combustion of any fossil fuel. It could be an engine exhaust where the flue gases are at high temperature. It could be a gasification system, like separate gasification system that is producing, producer gas or syngas. Okay, you're burning that producer gas for your heat. Okay, then so yeah, it could also be like over here. So you have the volatiles that are released from here. Okay, so as this is the torrefaction zone, the volatiles are released from here. So the volatiles are combustible, right? At least one portion of it, even though it is very small portion of it, it is still combustible. So you can burn that over here, and that can also provide the energy. Okay. or it could also be an exhaust. So exhaust gas, flue gas from power plant and so on. Okay. So now what we do is the flue gas or the heated stream that comes here is split into two streams. One for the drying, one for the drying zone, the other for the torrefaction zone. So could you tell me why do we need a heat exchanger here in the torrefaction zone, but not for the drying zone? So let me tell you this, heat exchanger is to reduce the temperature of the flue gas. So there is a, let's say water or something on the cold side. Okay. So it is taking off the heat from the flue gas. So why is that?
Because when it enters the second conveyor belt or the circular thing,
Here,
yeah, there.
it's not entering the circular thing. It's going directly to the torrefaction zone here.
Oh, okay.
You have to imagine this in 3D. This is the best representation we could come up with on 2D, right?
Sir, is this setup vertical or is
Yeah.
it flat on the ground?
It's vertical,
Okay.
top to bottom. Okay, so let me tell you this. So this is flue gas, right? So what is flue gas a result of?
Result of burning the fuel, the heat
Yes.
source.
Now think, a couple of days ago, we spoke about something pertaining to this. What was that? Something pertaining to flue gas. We spoke something specifically pertaining to flue gas or the products of combustion. What was that?
Like, is it related to gasification, like syngas or something? Syngas
I'm
producing
just
gas.
talking about combustion here. There is no gasification here, right? Flue gas is a result of combustion.
Yeah.
So we discussed about this at length. Something about flue gas. Let me also tell you this. It's about methane combustion that we spoke about. So you assume there is methane burning somewhere here and the flue gas is coming out.
It consists of mostly of carbon dioxide.
Correct. But what does that got to do with this? What is the requirement for this torrefaction? Think about that.
To cool it down quickly,
Cool what down?
the torrefied biomass.
How is the flue
Because
gas
it
cooling down
contains
the
carbon dioxide.
Sorry?
Because it contains mostly carbon dioxide, it
Yeah.
will stop the biomass from burning, from catching fire.
How is it stopping the biomass from burning? I mean, you're right. You're right. But then there's one thing you're missing out. In any case, there is no air here. So air is not going in here. This is completely air free. This zone
Okay.
is completely closed. And even in the flue gas, there's no air. There's no oxygen that is going in.
Yeah.
The heat is removed because it shouldn't go further pyrolysis.
It shouldn't go.
Like it shouldn't, like the temperature shouldn't increase much because then it would undergo pyrolysis.
Exactly. Right. So if you go further, if you have temperature of more than, let's say, 350 or 400 degrees, So this can be a maximum of 400 degrees at the outlet here. Because, I mean, there is the heat transfer efficiency also. So then the biomass will be at 300, 350, around that range. If it goes more than that, then it will get pyrolyzed instead of torrefied, and we'll be losing out on a lot of energy. Okay, so we don't want pyrolyzed biomass here. We don't want pyrolysis to happen here. We want only torrefaction. That's the reason we have a heat exchanger here. Now, observe on this side, we have diluted air. I mean, there is air dilution happening over here. So the flue gas is coming out here. Okay, and air dilution is happening. Why is that? I mean, you're just mixing it with air. Okay, just mixing air, basically. The ambient air at 25 or whatever temperature, they're mixing it with this flue gas, which is at high temperature. So you have a lower temperature. Okay. So the temperature remains below whatever 200, 100, 150, right, for the drying. And similarly here. Okay, so you have two streams for drying. My question to you is, why do we use direct mixing of air in this case and not in this case, where we using a water operated or air operated heat exchanger?
What's it?
The question is, on this stream, we are diluting the stream directly with air. We are mixing air with the flue gas to reduce the temperature. Okay.
Yes.
So physically mixing it. Okay. But in this case, there is no mixing happening. It's only a heat exchanger that we are using, so that the temperature is lower. In both cases, we need to lower the temperature of the flue gas. In this case, about 400. In this case, about maybe 150, something like that. So why are we using direct mixing over here, but only a heat exchanger here? Why not use direct mixing of air in this case?
Because if we mix direct air in the heat exchanger pipe,
There's no heat exchanger. I'm talking about instead of heat exchanger, if we use directly mix the air with the flue gas, what will happen?
Yeah.
Yeah.
So it will also contain oxygen, which might lead to its ignition there.
Exactly. Right. So that is the reason we are using indirect method of heat transfer over here, which is heat exchanger. And here we are directly mixing air with the flue gas. Okay.
Yes.
So there is a primary drying that is happening here while it goes on top of the conveyor, and then the secondary drying happens over here within the drying zone. Again, if you see here, there are like slits that are open to remove the moisture, and then a chimney kind of exhaust hood. So to remove the moisture, I mean, just dissipate the moisture. On this side, it's completely closed, so that there is no air, uh, air seepage into the zone. Okay, so this is the whole setup of the torrefaction system. So now we come to pyrolysis. What is pyrolysis? We already spoke about this at length. It's the thermochemical conversion of biomass in the absence of oxygen. Right? Pyrolysis occurs at a wide range of temperatures, starting from torrefaction, starting at 250 degrees Celsius. So torrefaction is also a form of pyrolysis, and it goes to about 700 degrees Celsius. So there are three products: one is solid, liquid, and gas. Right? The solid product is biochar. Liquid, there are liquid bio oils that are produced, and then combustible gases, that is the volatile gases that are produced based on the pyrolysis methods. So what are the pyrolysis methods here? So you have conventional or slow pyrolysis, which has a temperature of, 400 to 500 degrees Celsius, but the residence time is very long. And what is it used for mainly? And heating rate is very low. Okay, it's 10 degrees Celsius per minute, and it is used mostly for just preparing biochar. That's it. if you have seen in some places, what they do is they have. I have seen in Tamil Nadu, and there is a district, Ramanathapuram. Many of you might have heard of this district. So there are these trees that have, I forgot the name of these trees that have the thorns, right? That you see when while traveling in trains on the sides, you'll have these trees, right? So it's in abundance, and what the people there do is they just cut these trees, okay, and then they kind of ignite it, and then they limit the flow of oxygen by through inhibition by maybe putting some sheet or whatever, not sheet exactly, but some kind of inhibition they do so through sand or something like that. The temperature is high, but the seepage of oxygen is really low. So that kind of creates biochar, and that biochar they sell in the market or they use it for cooking and all that. So that is kind of slow pyrolysis where it should have long residence time and medium to high temperature. And yeah, the major products, of course, bio oil is formed. Here, bio oil does not mean it's an essential product. It's tar. Okay. And tar is not exactly useful for us, as we have seen in the case of gasification. Now, fast pyrolysis, it's a rapid thermal decomposition of biomass. Okay. And the heating rates are moderate to high, like around 100 Kelvin per second. Okay. Then you have, in this case, you have mostly bio oil that is forming. You also have some gases. Okay. And char is about 10 to 15%. That is the yield of char in this case. Okay. So the products like the bio oils are around 30 to 60%. Okay. And the gases are around 15 to 35% in this case. And the char is only about 10 to 15%. So flash pyrolysis, during flash pyrolysis, what happens is it's very high heating rate. Okay. And mostly we produce gases and bio oil only. We produce very little char, but then most of it is gas. Like bio oil is also very low. It has very high temperature and very low residence time, like less than 0.5 seconds. So it is more clearly explained over here as you go from slow to fast or flash pyrolysis, and as you go from low temperature to high temperature. So if you want, let's say, more of char, you have to go for slow pyrolysis and higher temperatures. Okay, so you'll have more char. If you want more liquid, then medium pyrolysis or even fast pyrolysis at lower temperatures, right? And if you go for flash pyrolysis at higher temperature, you'll form mostly combustible gases and very less liquid and almost no biochar. Okay. So what are the mass loss characteristics for wood chips, okay, at different temperatures? So you can see from 574 Kelvin till 676. So these are the mass loss characteristics. So one is like 100% of the mass is available. So if you see at lower temperatures, right, the mass loss is gradual, right? It reduces fast. Here there is fast reduction because of the moisture. Okay. The moisture is released, some amounts of volatiles are released, and then after that, it is very slowly, it reaches about what, 50%. So there's 50% mass loss. As you come to higher temperatures, if you can see the 676 Kelvin, it is a very rapid mass loss. Directly, it comes to about 25%. And then after that, it kind of stabilizes because there is char formation, right? There is fixed carbon, which is not very easily degradable. Okay. So in this case, you are able to reach like about 25% or 75% mass loss, right? So you have only 25% of the mass remaining in the biomass, or at this point, it is only biochar. So coming to this pyrolysis versus heavy fuel oil or crude oils, right? Petroleum crudes. So normally the bio oils have high moisture content. They have high oxygen content. So it is quite volatile. It can react very easily. It can polymerize. And so because of the high oxygen content, it can lead to oxidation reactions. Okay. And if you see it is heavier than water actually. So specific gravity is 1.2. So it is heavier than water, whereas crude oil is lighter than water. Okay. And if you see the viscosity also, viscosity is lower, okay, compared to the crude oil. And the solids are almost the same. Okay. And the distillation residues. So when you distill bio oils, you have up to 50% residues, whereas in this case it's only 1%. Okay. So bio oil cannot be used directly. It has to be subject to some other chemical processes like transesterification or esterification, not transesterification. Yeah. So esterification is you I think it's you mix it with methanol and then with an acid, I think sulfuric acid or something to produce some kind of biodiesel. So that's what happens, which can be blended with diesel for automotive purposes. So I'm not exactly sure on the esterification process. Yeah, you can look it up. So the pyrolysis produces biochar, right? And biochar is a porous substance. And what is the use of biochar? So biochar can be used for water treatment. Okay, not treatment exactly, water filtration. So why is it so useful for water filtration? Because it has so many micropores that all the suspended particles or most of the suspended particles can get trapped in these micropores and you'll have clean water out. Okay. That is the use of all these porous substances. It can also be used as a catalyst in many reactions. Like, for example, if you have uh, a mixture of gases, okay, that has carbon dioxide, if you want to separate the carbon dioxide. So if you pressurize the gas to more than 12, 13 bars, something like that, then the this char has high affinity to carbon dioxide. So the pores will trap the carbon dioxide and will let the other gases pass through. It has lower affinity to certain other gases. Let's take biogas, for example. It has low affinity to CH4, but high affinity to CO2. So you'll get pure methane on the outside. Okay. So it is a very good adsorbent, right? So what are the advantages of pyrolysis? So one is, of course, the carbon neutral route, the utilization of renewable resources through a carbon neutral route. Utilization of waste materials like, sawdust, forest thinnings, barks, and so on, and agricultural residues. Self-sustaining energy. How is that? And multiple useful products. We've spoken about this, but I would like you to name them. So how is energy self-sustaining in this case, in case of pyrolysis? Like, let's say you want to build a pyrolysis reactor, you need to provide energy to the reactor because the pyrolysis is an endothermic process. So how will you create a reactor that is self-sustaining in energy? Anyone?
You have heat exchangers.
How? You have to heat it up, right? You have to heat up the reactor for the pyrolysis to take place. So where will that heat come from?
When you cool it down through the heat exchanger.
How are you providing the energy required for the heating up? That's my question. You saw during torrefaction what happened. So it's very similar to that. Just recall that. Recall what happened during torrefaction.
A percentage of biomass which
Mhm.
is uh, which can be used to generate the heat also, like as a heat source.
That is
Similar
okay,
thing
but
is
that will still be counted as an external heat source and not internal.
okay.
There's something during the process itself that happens that can be used. Can you guess what that is?
Like you're talking about self-sustaining energy, right? Like how it
Yes.
is.
Yes. This is one thing. Okay. Using the same biomass to, heat it up and so, but that is still external. Okay. Think what is released during pyrolysis,
Volatile gases.
which are
Um,
You can combust them again. Use
exactly.
that
So you
heat.
have carbon monoxide, hydrogen, and CH4, which are combustible. Although they may not be in, I mean, mostly CO2 will be in a much higher proportion, but that's okay. The mixture of gases is still combustible. Okay. So that can happen.
yes.
Okay. And like you said, like we can use biomass as another external source of energy to supplement this uh, you know mm, volatile gas based combustion. And what are the useful products from the pyrolysis? I mean, we just spoke about all this, right? What are the useful products? It's literally just a couple of slides ago.
Oh, the useful products of pyrolysis.
Yeah,
Um, Clarified biomass, does it come under pyrolysis?
sure. But
Yes.
okay, but that's more of a raw material than a product.
Oh, okay.
It's a raw material for the
So
next process.
electricity, useful products.
No, electricity
Electricity.
is not a product of pyrolysis, is it? It's not at least a direct
No,
product. I'm
heat,
asking about direct products. Hmm?
heat, and
No,
different
heat again is not
volatile.
a direct product, right? You
Yeah.
can
Okay.
produce heat
Volatile
from the
gases.
products of pyrolysis.
Yes. Yes.
Yeah.
Volatile
Volatile
gases.
gases, yes, one. Second,
One of the products, and biochar.
then yeah, one more. You missed one.
Moisture. It's
How
not
is
useful.
moisture product?
Yeah. It's
Remember solid, liquid, and gas. Yes, oil, bio oil, right?
bio
That can be
oil.
further
Yes.
processed into, uh, diesel, biodiesel, or an additive to diesel, basically. Okay. So these are the products, and then you have, conversion of low energy biomass into high energy density liquid fuels. So that happens during pyrolysis. So these are some pyrolyzers, fluidized bed pyrolysis, right? So what happens is we have seen the fluidized bed reactants for gasification, and this is for pyrolysis. Okay. So the difference between this and this is you have an indirectly heated pyrolysis chamber. So where you have the feed and this entire thing is fluidized, which means suspended in the air. Okay. And there is heat transfer material, which is sand. So that transfers the heat to the biomass. okay, in the pulverized form. And the volatile gases and literally everything is traveling to the cyclone, right, where the solids are separated. Okay, so the char plus the heat carrier, which is the sand, and the gases and liquids are kind of, and in fact, there is no liquid at this temperature. So even the liquids, the bio oils are in gaseous form, in vapor form. So they are transferred further into a quencher where, there is the bio oil comes down, and condensable bio oils are further taken to another condenser. So the temperature is further reduced. So you have the lighter fraction of bio oils that are coming out here, and then the heavier fraction. Sorry, I mean the gases are just released. Okay, and over here there is some. There is a burner, so that is what provides the heat to this to the heat carrier, and then they are again transferred to the pyrolyzer. So in this case, there is no circulating loop. So whatever goes here, I mean, along with the gases and the unconverted solids, the char and ash are just removed from the cyclone, and the bio oil plus the gases are, sent to the quencher and then the condenser. So you have one heavier fraction of bio oil and one lighter fraction of bio oil. This is very similar to the distillation that you see for crude oil, basically, right? So this is what happens in pyrolysis. So you can uh, read more about this at this website. Okay. So yeah, that's it. I think this is the first day we've completed before time. So that's a new achievement.